the point of this panel is for all of you to ask questions of the panelists. Often I ask the maybe first question to get started, but I don't need to do that. If somebody has a pressing question that they want to ask our panelists on anything that they've heard today, or even basically related to numerical packages and software, I'm happy to start with a question from you all. But the point of the panel is to have you ask questions. So does anybody have one off the top of their head right now? I'm sorry? Wave. Oh, yes, go please.
It's really quick. I just wanted to make sure, is Sundial supported in Fortran stuff as well? Okay.
Sundial supported in Fortran, okay. Exactly the kind of questions we want. And I'm going to hand to the...
That's a lead into. You said, God, I hope not, when asked if there was Fortran. I think you should elaborate on that.
So I'm going to hand the mic to the panel. Please, panelists, all pass it among yourselves. I am going to try to keep your responses to 90 seconds, so you can ask more questions. But so yeah, Jonathan, go ahead.
I guess that was probably that was more or less flippant. Let me put it that way. It's I think that for the purposes of Trilinos, the interoperability with Fortran has always caused us a bit of problems just with compilers. So that's, yeah, I think if we were all Fortran, that would be great. But we're not.
Anybody else have any comments on Fortran in general? Or well, let me maybe a question worth asking is how many of your packages support Fortran interfaces, and do you see Fortran as a key technology in what you do?
So PETC provides a more or less full interface to Fortran. We try to have almost all the functionality match. And the way we do that is by having these kind of artificial objects in Fortran that match the C objects. And so all the code's written in C, but you use it almost exactly the same from Fortran. Since everything is object-oriented, you never look at the data structures. It doesn't really matter what language you're working with.
Did you have a comment, Dan?
So Sundials is very similar now. It used to only have these legacy kind of Fortran 77 interfaces, but we are about to actually have the release, but we had betas out for a while that use full Fortran 2003 interfaces via SWIG, and it's actually built off of what Trilinos had already been building for Fortran 2008 interfaces for their C++. So we put those in for ourselves as well, and it's essentially all the function calls look just like C with an F in front, and yeah, it's very object oriented, just like Barry was talking about. It's not for Trilinos, but it's a Fortran fork of SWIG that Kate Evans is working on for you guys.
Real quick show of hands of people here. How many are doing a majority of your work in Fortran? Maybe a quarter. Okay. All right. Other questions along that line? Fortran-wise, language-wise? So let me ask the panel. What language or languages do you do most of your work in?
So you've been hearing about ECP, the Exascale Computing Project. And so as part of that, we're all supposed to be getting on the new machines, and we're supposed to be some of the earliest adopters. And if you ask who writes the compilers for these new machines, it's the computer scientists. And if you ask what language do computer scientists work in, it's not Fortran. And so one of the things that you'll find is for packages who support the world, yes, we have to talk to Fortran, but the compiler support for Fortran, I'll make does and will always lag compiler support for C and C++. And so you can fight that battle over and over and over. If you ask, depending on who you ask about compiler support on the new machines, Fortran, yeah, we're planning to, sure, no problem. So one of the things that we've gone to is we've said, okay, we're stripping Fortran out of the guts, because that way we don't have to fight. CUDA Fortran currently requires PGI. PGI is not necessarily your friend. Try to be controversial. Anyone want to react? That said, for people who are C and C++ phobic, we maintain a Fortran interfaces where we wrap the C++ objects in Fortran interfaces so that somebody who wants to program entirely in Fortran doesn't actually have to see a semicolon.
Yeah, there's no semicolons in our code either,
In your whole code?
in the Fortran code.
Right. Yes, later.
Okay, so please, if any questions come to mind, go ahead, grab my attention. I might not be looking in your direction, so definitely grab my attention. Oops, that was your timer, Ann. Yeah.
Oh.
No. Oh yes, go ahead.
So, since you mentioned PGI, you know, I've used a little bit of OpenACC in the past, which seems to, you know, not be heading into the future. What are your feelings about the best way to target GPUs in a cross-platform way, not just targeting, you know, NVIDIA GPUs, especially since our two new big machines are not going to have NVIDIA GPUs?
Okay, so strategies for dealing with GPUs?
Yes.
Yeah.
I'll start. So our project has the luxury of having some really knowledgeable programmers. So we are going with, on the NVIDIA, we're going with a relatively pure CUDA approach. It looks like the CUDA to HIP. So for those who, Summit has NVIDIA GPUs, NERSC has NVIDIA GPUs, Frontier will have AMD GPUs, and Aurora we know will be, okay, I think we all, I'm trying to remember what we know officially. We know Intel accelerators. So we know that AMD is going to support HIP. HIP is very CUDA-like, and in fact they are tools that appear to do a really good job. So the CUDA to HIP move is not a big deal. So if you're in CUDA, you're going to be fine on AMD GPUs. Intel is anybody's guess. But OpenACC, OpenMP have their own issues, shall we say.
So let me interrupt you. So you identified a number of technologies that
Yes.
you're having to confront. What are the strategies you're using to deal with that variability?
We are reducing the variability in the sense that there's OpenACC, there's OpenMP, there's multiple compilers. We are, in some sense, choosing a swim lane and sticking to it.
Okay.
Right. And I think it's a path forward, but that's with the luxury of having a team of people maintaining an infrastructure.
Okay, other panelists?
So what is that path?
What is that path?
Yeah, you didn't officially say.
CUDA as opposed to OpenACC/OpenMP. CUDA leading to HIP, which we believe is going to be a viable path
So the application programmers will be programming in,
in AMRX.
which is, so they'll be basically programming in C++.
Yes. Yes.
Okay, so just to clarify that, your customers
Yes.
talk to your framework, and your framework handles the porting issues, the
Yes.
performance portability issues. Okay, how about you?
So you have, I'm just trying to clarify a little bit more. Basically, they write in C++ and you have templated organization to take it down to CUDA
Yes.
or HIP or so
And they
forth.
write actually Fortran kernels that can get called in the right way. But AMRX
Okay.
itself is going to be Fortran free. We will support calling Fortran kernels.
So the first thing I recommend is write as little code as you can, use libraries as much as possible to do the bulk of it. So PETSI's adopted this model that because we're object-oriented, we can have multiple backends. And we have a backend at the moment that's OpenCL, we have a backend that's CUDA, we'll have a backend that's HIP CUDA eventually. We may need another backend for the Intel systems, or we may not, we don't know yet. But the idea is that all of that code is in the library. You don't need to access it directly at all. And so you can choose either to work with a lower level thing like that, or you can choose to work with a higher level thing like OpenMP, or maybe what Intel is going to be offering for their machines. Now, the only reason you would choose to use something like OpenMP is because we provide much of the infrastructure. So you don't have to write a complete infrastructure. Essentially, it's actually not terribly different from what Ann does, is you provide more or less your function evaluations, your Jacobian evaluations and so forth. You don't have to write a large code that manages meshes, manages discretizations, and manages all of that yourself. You just provide the little pieces that are unique to your problem in a very different way than you provide it to Anne, but fundamentally it's the same model. And the key is we want to give you the flexibility to provide it in a variety of different ways based on your choice, because the back end doesn't have to match the front end. I could probably go on, but let's move along.
Yep. So for Trilinos, we're going to be using, at least the libraries will depend on Cocos. They already do, and that'll be sort of, we're pretty lucky because we've got a lot of the core Cocos development team at Sandia. And so they can provide a lot of the back ends for the different machines. So we just have to write to Cocos.
Now, have you heard about Cocos already? Or okay, so you're familiar with that as a portability layer. Okay.
So for purposes of this panel, I'm representing our efforts across the community in collaborating. Talked about that this morning. And so I will just say that this is a very open question. As you've heard, we have a variety of different approaches that different teams are using. So we're in the midst of dialogue among the whole community to figure out how then we can continue to interoperate among our tools. So it's an exciting time.
Do you have a sense, Lois, of how much like if Petsy chooses, this path for dealing with what I think you mentioned OpenMP at some point. So some caller is using OpenMP to talk to Petsy. Does that then present problems if other packages within the XSDK ecosystem are also providing some GPU portability, but perhaps using a different mechanism?
Well, to be honest, it depends on exactly what's happening and how it's happening. There's no crisp answer to that.
Okay.
So.
The vendors have not completely answered the question of how much interoperability they provide. They're making some indications that they will provide some interoperability, but it's not always clear yet, and they haven't made definitive statements.
Okay.
And I'll just say we're doing similar to what Petsy is doing in that all of the parallelism that happens inside of Sundials happens inside your vector and matrix operations. And so we have a bunch of back-end ones of those, and we're building a HIP one now. We have CUDA ones, Raja as well. We're going to build a Cocos one soon. So there's a lot of that back-end work on our end so that you guys don't have to do all that. But of course, you have to write your ODE describing right-hand side, and that has to access the data. So you need to be able to be familiar with how those work.
Okay, follow-up questions on the GPU topic? I see a hand here. We'll come back to you. Okay, go ahead.
So this is a very short question because I think Anne said right at the beginning, she was saying that OpenMP and OpenACC have issues. I assume you're referring to when restricted to talking about GPUs, but I was just wondering what issues were you thinking of with OpenMP and OpenACC? Because you said you said Amrex uses CUDA and HIP, and you said there's issues with OpenMP and OpenACC.
Go ahead, take the mic.
So I've heard OpenACC developers say that the goal of OpenACC is to become obsolete. And and that's a positive. So I very much believe in what OpenACC is doing, which is trying to push forward a certain way of doing things that then gets incorporated into language standards. So I believe that is a very, very good thing. I think that, so one of the things is that when you look at the machine and the available compilers and the available versions of the compilers and the the versions of the GCC or the PGI and the version of the OpenMP, you end up with a lot of combinations. So I will say that one of the decisions that we've made is to reduce the number of combinations that we're going to support. OpenACC it's not a bad product, but we don't see it as a long-term strategy. OpenMP has compatibility issues between versions that make it hard to support all versions. So in some sense, what we've decided is to simplify the statement of what we will support.
All of the major vendors have been saying strongly that they're going to support OpenMP for their machines. None of them say anything about OpenACC, so keep that into account, even though OpenACC is actually far better design than OpenMP. none of the vendors, Intel, NVIDIA, or AMD, has said
Sorry.
we're going to be supporting this technology.
So
They've
sorry,
all said they're going to support OpenMP technology.
So you said that you think OpenACC is a much better design, even with the new stuff, the way that the new stuff's been incorporated in OpenMP 5 for
Yes,
GPUs?
absolutely.
Okay. That's
The OpenMP 5 has the same drawbacks that the 4.5 has and all the ones before that. Being completely pragma-based is an enormous limitation, and it's especially a limitation for when you try to develop libraries. That's why we're never going to write any library code in OpenMP. It's just not amenable to libraries with a pragma-based system.
Okay, you had a question,
That's
follow?
okay, yeah.
Oh.
So kind of going off what you were saying about CUDA and HIP, how risky is it? Maybe this is unanswerable, but how risky is it for us to just go all in on CUDA and assume Intel will provide a HIPify-like tool in the future?
Intel has given no indication that they will support anything like CUDA, publicly.
And the flip side of that is Intel knows that people are buying into CUDA, and so, I mean, AMD's made a smart choice, right? They've said we're not calling it CUDA, we're calling it HIP, but we're going to give you. We know that you're coming from CUDA, so they've provided, I don't know if they're translators or. It is very reasonable to go from CUDA to HIP. Intel, like I said, they're not talking, so people can speculate what it will be. In some sense, you could argue that they should do what AMD doing and provide a pathway. That makes a lot of sense if you want people to run on your machine. That said, they haven't said. So we're all kind of waiting and wondering, I would say.
Isn't that weird? Because the DOE decided, yeah, we're going to put, I don't know how much million in Intel and say, okay, let's do whatever you want and we'll see when the machine is here.
Hold on, Lois, take that one.
So just to repeat the question,
No comment.
why has DOE put so much into Intel, and is that what you're saying?
Without answering or
With-
without asking for something in return.
Without asking, okay.
I'm,
Great question.
none of us really are in a position to comment.
Yes, go ahead.
So, sort of, before we had MPI, we had all sorts of different ways of doing distributed memory programming, right?
Right.
We sort of seem to be in the same boat again. So what can we do to sort of make something homogeneous, maybe part of the language standards or some other standard that we can all use to move forward?
That's a great question. I would say that already there are a number of rich conversations that are happening in the community generally. So, the time is really ripe to see whether, we can begin to move forward, because this certainly cuts across many layers of the system. We as math libraries people can't be inside a little bubble and solve this just for ourselves. We all, across the application space, the programming model space, need to figure out how to move forward. So, I don't have an answer.
But just to follow up that question, if you look back at when MPI was just sort of coming into being and the MPI 1 spec was being adopted and vendors were starting to pick it up, what do you think happened during that period of time that made MPI successful and the other technologies not so much? Anybody have any thoughts on that?
Barry remembers this.
One is definitely a portable implementation that pretty much worked everywhere.
And that's
And without that,
MPitch?
that was MPitch, and that was developed as the standard was being developed. So not only could everybody use it immediately when the standard came out, but they had already worked through the bugs, worked through design issues by having a real implementation. You can design something in your head, but when you actually use it, you realize all the problems that you have going along.
Sorry.
In addition, at that point, because of this, it wasn't reliant on vendors actively doing something quick. So the thing with new compiler technology, say we want to add this to a compiler, you have to convince several different compiler writers to actually do this, because it's impossible for any group independently to do something like that. While with MPI, it was possible for a group to actually write a library like that.
Okay, so that's actually key here, is that with the issues with GPUs, it's so much more tied to the compiler technology that the vendors are sort of in the critical path.
We don't know.
Okay.
Maybe there's good abstractions that don't have to go that far. Like, for example, what Ann is doing, what Cocos does, where you take a really rich templatable system, C++, you can make it go to many different things. With a good starting point for the design and good coders, you can map it down to many different things. So even if Intel goes with something that's not all that much like CUDA, almost for sure, Cocos is going to map to that pretty well. And they'll spend the time to do that. So that is one model of using the C++ template approach to go down to all the details that actually matter on the GPU, independent of the details of the GPU and the exact programming model for the GPU.
Other panelists have comments on that question?
I'll just comment that, I think Raja might do the same thing, but there are Cocos developers who are on various standard committees who are, in some sense, maybe they're trying to make themselves obsolete by getting things into the standard, right? And then
That's how we want it to happen.
yeah, that's right. And so I suspect they're not unique, that there are other folks who have staff members on the standard committees and are trying to get things into the standard. So
One thing I know that, at least in the past, they did with Raja is they kind of used it to shame different compiler teams into submission over why aren't you guys doing these loops right or that loops right. And I think it moved them all forward a few steps. Yeah. Okay, I'm probably not looking for hands. Other questions? Yes, you.
Hello. So you agreed to the standards. How do you qualify that the software which are in this package satisfy the standards?
So you're talking about our community policies. That's a great question. So we as a group has discussed and defined some community policies, and if you look at the XSDK community site, you could see there's a pointer to a space where each package indicates the way in which they've chosen to respond to each community policy. So each package development team provides that information, and then the other members of the community evaluate that, look at it, and make sure that that it makes sense. So, excuse me, could you say that? Repeat that. The question is, do we do a reviewing process to determine whether packages who say that they're compatible with the community policies actually are? So the short answer is yes. Informally, we communicate among the package development teams to take a look at package compatibility approaches and to look at the software and make sure that things are compatible.
And well, in fact, is that at all formalized in essentially any sort of testing? Like when several packages say they interoperate, there's some sort of thing that at least tests that they all build with the same build flags and
Absolutely. So testing is essential in order to ensure that our software works effectively. So to become a member package of the XSDK, a package must satisfy the compatibility requirements and either use or be able to be used by another package that's part of the full set. And that interoperability needs to be tested regularly for regressions. Looks like Barry has more comments.
This is a good way to segue into a different topic that I hope we spend more time on later. That's very important, but in this specific instance is still important, is the standards are something you see on the web, the responses by each piece of software on the web, and the software is on the web. It's not the responsibility of a little committee to make sure that the standards are followed. It's actually the responsibility of the community. So if you get one of the packages and try to use it with another package and it doesn't work, it's also your responsibility to try to contact the developers and say, it doesn't work in this situation, can you help me? And if they're responsible members of the community, they'll actually say, we promised this, we're going to try to satisfy that, and they'll adjust things to do that. If the community doesn't do that and you just leave it to a, quote, committee, then of course, committee's going to be overworked with other things. They're really not going to work that well together. People are going to say they satisfy their standard, but here and there they might do something slightly different because no one noticed, because it's hard to inspect the package. The only way you can really inspect a package is by using it. So it's actually all of our responsibility when we see other packages that we don't think are doing the way we think they should be doing. is to be proactive. Contact their issue site or whatever and say, yeah, in this circumstance, it doesn't work the way it seems like the standard says it should work.
So you, go ahead, Ann.
So two comments following up. So one is there are certain standards that are designed for interoperability. Things like you have to be willing to share the MPI communicator. Things like you have to have your own namespace. So there are a lot of things that are good software practices. They do not guarantee that AMRX can just call PETSI. AMRX had to write a bunch of code to interface with PETSI. So the fact that we're both in XSDK doesn't mean that interface exists, but it means there's potential for it. In this case, it does exist. So comment one is it doesn't guarantee that interoperability exists. It guarantees in some sense that it could exist. But comment two was if you had seen the behind the scenes chatter leading up to this workshop, you would realize that this is literally a daily process. I should put, where's Satish? Oh, there he is. So I should put Satish on the spot because Satish is kind of the go-to guy. So Satish, I tried version 5.6.0, but this wouldn't build. Satish fixes it. Oh, but Satish, I tried this version with this compiler, and now this happened. Satish fixes it. So, I mean, literally, up until what, yesterday? At least Saturday night, I know. Don and Alp are working together. You'll hear from Alp later. Lot of back and forth. You do not know how many Zoom calls and emails and everything to make sure that what we showed you today would actually execute. We won't get started on the Viz packages. So there's something that I'll touch on later in the wrap up, but there are a lot of very well-intentioned people working on this, and we are literally doing, okay, if not daily, at least weekly, we are trying to manage the complexities of this, the compiler version, the AMRX version, the PETSI version, the machine just got an upgrade. It is a moving target, and so it's, in some sense, there's an investment to staying up with it, and the idea is that the payoff is worth it. The payoff is that you don't have to rewrite your code 3 times every time there's a new compiler or a new whatever. That's what all these software libraries are trying to give you as a layer of protection against that. We are working towards this easy compatibility and interoperability. We're not there yet. I would say moving target's the best description.
Yeah, just and thanks for saying that. Just to essentially paraphrase, using the codes that you're talking about here, other packages that you've talked about, is like becoming a member of the community that uses that. And not only when you're having issues like maybe with bugs that you mentioned, Barry, or compatibility, but if there's a feature that you think would be really important for the package to have that would advance your science application, go ahead and make sure the code team's aware of that and understands why it would be important. It's starting to get involved in that sort of collaboration effectively. In fact, maybe some of you can speak to this, is as you work on these packages or have users that have worked on them, how often do some of your users ultimately become collaborators and developers? Does that happen very often in your packages?
I mean, I think that's a pretty typical thing. Like, for example, we'll have people come in, summer interns, for example. They come in as users, and if we continue having them come in and use parts of Trilinos, then gradually they become power users, and then hopefully a developer. A power user? I guess it could be, sure.
Anyone else want to comment on this point?
So this is, I think, very crucial to understanding HPC and software is there aren't two worlds. There isn't the world of the people who write the libraries and the people who use the libraries. It's just one world, and people move back and forth between them. And many people are comfortable moving back and forth, and by moving back and forth, you actually contribute enormously to both sides that you can't contribute on one side or the other. So you shouldn't think of this library as this alien thing that just popped up there and you have to use it exactly the way it is. It's written by normal people just like you and adjusted by normal people just like you as time goes by, and it's absolutely crucial to understand that. It's not a canned package from Microsoft where you're just stuck using it the way it is. So most of the PETSI developers are people who used PETSI before they knew us. And Satish is one of our first users, and he was great, and we said, hey, we're going to hire you. And many of our developers who don't work at Argonne just started using it and realized it can contribute. So I think it's useful to think about things in a couple of different steps. The first step is realizing when you're using a package that the package is not perfect. There's things that can be fixed, there's things that can be improved, there's things that can be added that don't exist there now that would complement what's already there. So the first step is realizing that, and you're a person who can recognize that by being someone who uses the package. Almost always you're going to be, you know, Ann had a great idea, but I want to do X and I can't quite do it. And so the first step is realizing, you know, it may be possible. The second step is realizing, hey, I can do it. I can actually go and add a little bit to AMREX or PETSI or Trilinos or anything. And not only will I benefit, but other people will benefit. Now the hard step is step 3, actually doing it and then getting it into the software. And that's a very interesting step because it's not just technical, it's also handling how do you contact the developers of the software, how do they handle pull requests, how do they test contributions, how do they decide whether contributions should go in and so forth. And all of us are still learning this, I would say, from the point of view of really knowing how to manage pull requests from other people and test them and accept them and so forth. But we're all eager to do that. There's nothing better than a user who contributes to the package, actually. Users are great, but users who contribute to the package are fantastic because not only do they benefit and we benefit, but all the other users benefit from the additions that they've made.
Yes. I'm looking over here. I just want to make sure I didn't miss any hands over here because I'm not looking over here too often. Anyone? Okay, go ahead.
So in academia, it seems like testing, documentation, verification, validation, those things are sort of, I mean, it's not really what they pay us grad students for, right? They pay us for scientific output, papers, et cetera, right? So what can be done to try and improve the quality of software in academia, and like how can that sort of become part of our day-to-day job?
Number one is contribute to a package that actually is actively doing that, because they already have a testing infrastructure. They have a philosophy that when we incorporate something, we want it to work and so forth. Trying to do it all on your own is very ambitious. And it's great to be ambitious, and some of you should be ambitious and do that, because every graduate student who comes up with a new package becomes, 20, 25 years later, PETSI or Trilinos or Sundials or whatever. But in addition, by working with other people who already have a system, you can gain a lot of the testing infrastructure, the basic coding style and all that stuff from that package. So PETSI, for example, we do a lot of testing on a lot of different machines. I mean, we still test on Solaris, for example. And the point is, the more obscure you test on, the more obscure things you find that are wrong. A graduate student can't test on Solaris unless they're crazy. But by working with a group that has this infrastructure and contributing, that's the way you can take advantage of their testing abilities and so forth that you wouldn't have on your own. One more comment that I realized that I didn't make earlier that I think is really useful. A lot of people also, their first pull request to PETSI is, I noticed on this manual page, you don't explain anything. So I've added some text. Can you take a look at it? And that's a fantastic way to start because it's not nerve-wracking in the sense of when you add code, you're like, oh boy, is that code going to break in 3 years and embarrass me? When you start by just making improvements to the documentation, it's really clear this is valuable because we didn't say what we used to say, and at the same time, it's pretty easy because you don't have to worry about the testing and so forth. So that's one thing to think about when you're reading our documentation, and frankly, all our documentation is of lower quality. Some's a little better than others, but none is great. And that's because we have so much else to do. We don't have time for this. When you read it and you see things that are wrong, let us know. And the best way to let us know is with a pull request. Because when we go, you're absolutely right, thank you. Certainly with PETSI, and I think all the other packages are starting to do this more and more, every commit will always say the person who contributed. So even if you fix a misspelling in one manual page, that commit will give you, it won't be your commit, of course, if you make it, but it'll have your name on it. Thanks for the correction.
Contribution bragging rights.
So I've had this discussion with faculty members of saying, it would be great if you guys use this stuff. Oh, well, no, we want our students to learn. And So there's this trade-off between, I mean, I've written my own multigrid solver more than once. I could probably sit and write one this afternoon. Is that a good use of my time? No. So there's something to be said. I mean, in classes, obviously, you write code, and there's something to be said for doing a certain amount of it yourself. Where exactly that line is, I think, is hard. But things like, I mean, multigrid is a really, vanilla V-cycle geometric multigrid is a really, really straightforward thing. 1 million people have done it. It's not a bad, something like that. Well, gosh, professor, what would you think if we swapped in this package? I think it's probably going to take some initiative on the part of somebody who may not have any extra time either. There are trade-offs, right? You probably can't embrace a whole package, but the thing that we'll come back to, because I get to do the wrap-up, is you have a finite amount of time. And so where do you want to spend it? And the thing I would ask is, there's something new. If it's your PhD, there's something new in it. That's hopefully the definition of getting a PhD. There's something you're contributing. It's probably not vanilla multigrid. And so if you can make that part easier so that you can focus on the parts that are new and interesting, you win. There's a price. There's a startup price. You rally hopefully 5 of your favorite graduate school friends and say, hey, let's do this. But I've seen faculty members really push back because they feel like if you, quote, just use a package, you're not learning anything. And there are trade-offs. You use it as a black box, you've missed out on something. That said, we don't have time to all reinvent the wheel.
So the last question, did you have something to add?
I'd just like to make a quick forward reference to the session that will take place here on Thursday, where you'll be focusing on software productivity issues. And so there'll be some good conversations here about low overhead ways that all of us can try to improve what we're doing with productivity.
So, yes, go ahead.
On the similar thread, what are your thoughts on publishing the open journals about just strictly software versus?
You mean writing publications that are talking about the software?
Like the Journal of Open Source Software,
Right,
for
right,
example.
right.
So the question is, what do we think about giving credit to people through the, well, my personal opinion is everybody should really be getting full credit for the hard work that we're doing to write great software. So broad initiatives in the community, such as journals, such as JOS, are really taking some important steps forward to create opportunity for software to get recognition and thus somehow count in all of our career advancement, which is important to continue to raise the profile of the important role that software plays. Really, it's how we all do our work. We encapsulate our expertise, and it's how we communicate and do our research.
And I'll note, things like that are one way for us to get academic credit for documenting our code and making it clean and shareable. Because in many of those, you actually have to have either the Git repo available or some way for people to download it so reviewers can look at it. And so, I think it is tough as an academic to get credit for all of the documentation I write. It's very, very, very challenging. But there are other benefits you can get, and as long as you can try to leverage those things. So publishing about your software, it might not be as great as a science paper, but it's still a notable publication that'll be on your list. And so I think it's good to clean things up enough so they're reproducible enough so you can publish in that way, and then move on and get your science stuff as well.
Yes.
Yeah, I guess just follow on that, and with more and more complicated heterogeneous hardware and software package, do you foresee in the future that scientists actually have to make a sort of a choice between do the actual scientists use those packaged software versus actually start writing and get hands dirty and get significantly involved in those software?
I'll point out that it's no different than the 50s and 60s. The exact same decisions had to be made because people, of course, knew software and hardware much less. They, at the same time, were thinking these trade-offs. Do I have to write in assembler? Can I write in a high-level language? Can I write in a portable way? It, frankly, was no easier to program when the, quote, machines were simpler than they are now, because they weren't really simpler. They just had different limitations. So I don't think the trade-off will always be there. I don't think it's worse now than it's been in the past. And it's clear that in the next couple of years that GPU-type accelerators are where everything's moving to. After that, who knows? But it could be that for the next 20 years we're using basically the same architecture. Or it could be only 3 or 4. We don't know. We don't have the answer to that. 25 years ago, would people have people had told me, oh, you're still going to use basically the same MPI and the same programming model. 25 years is a really long time, and that's how long it's lasted. So there's nothing that says fundamentally where we're moving to now may not remain the same for a while. Or it may change. We don't know.
Yeah, did that answer your question? Or,
For the most part.
oh, okay.
So there's a flip side, and I think people like us probably debate this over beers because none of us knows the answer. But you can envision something like if you look at instrumentation in observational and experimental science, they don't let just everybody run the fancy machines, right? So you can imagine a world where the software and hardware stack, that entire stack is the specialized machine, and the scientist who wants to run the simulation has to go through, a quote technician or whatever it is. You can imagine that, but there are also a lot of people who aren't going to be doing science on the biggest, the most advanced machine. So I think we're always going to have people doing science on a variety of architectures. Whether everybody in the end will run on the most cutting edge machine, probably not.
So we had a question over here.
Yeah, I just had a quick question about, I don't know if I know how to verbalize it best, but so this workshop was kind of an effort to help make sure that we don't really have as much of a leaky pipeline of people who want to work on HPC applications of problems. So I'm curious what your thoughts are on like where other sorts of leaking is occurring. Like, do people who are starting to study coding, I mean, that's a big push that we have people who understand it a lot more. Do we also need to start trying to encourage thinking about things beyond just serial computing and at an earlier age when we do sort of outreach? I don't know. I don't know really how to mention it besides like where else on the educational pipeline or outreach pipeline does this really, have you seen this really matter? Or work.
So when you say, when you refer to this really matter, is it the becoming conversant with the technologies that you're talking about?
Okay. Beyond just like being able to do low-level coding.
Ah, okay. So so there's programming and just learning how to program, and then there's learning how to do, basically science with the packages and tools that are available to us.
That's a better way to explain it.
Okay, and so your question is more focused on are there other aspects of learning to use these packages to do real science that are sort of not on the table right now?
No, I think my question is, do you see people being turned away from working on these sorts of problems at a certain point as they're learning how to?
Maybe getting frustrated?
Yeah, exactly. Do you see people being turned off on that? And what are the sort of like low level or like earlier in your education on these sorts of problems? Interventions that could actually occur, or other ways of thinking about, like when you're learning programming and science, computational science problems, like to start thinking about it differently in an earlier age.
So how to keep, maybe the question is how to keep people excited and not getting, maybe reaching a point in their career or education where they just become frustrated maybe with the tech, because it's quite complex, and it's getting more complex all the time.
That's a great question, because to do high-performance computing with applications and interesting machines, you're juggling a lot of different concepts at the same time that you have to keep balanced in how much you keep track of them. Do you spend too much time worrying about learning details of a language, too much time on the science, too much time on the scaling, and so forth? How do you balance all those pieces? And I would say for a lot of people, our brains are not designed to balance so many things. We're designed to focus in on one or two things. At this point in history, to work in this area, you have to be good at balancing a lot of things. And if you're not, you're going to be very frustrated because, oh man, today I have to learn this. Tomorrow I have to learn this. The next day I have to learn this. I think to all of us here, and probably a lot of you, we love the diversity. The fact that you actually have to know this, this, and this. It's not all just one particular thing. So to be able to keep a lot of different ideas in your mind at the same time that are related. How do we bring that into earlier education? That's a really good question, and I'm not sure. We do see a lot of, quote, kids today who think of interacting with the computer as just punching on a GUI and don't think about, well, what's happening underneath? And if you just punch in the GUI and you don't care what's happening underneath, you shouldn't be in this room, you shouldn't be an HPC. You have to be someone who's driven to worry about what's underneath and to say, I wonder what's under there, I'm going to poke around and find out.
Well, how when you say that, go ahead. Yeah.
Okay, so I'm a
Oops,
big.
sorry. Go ahead.
Cut me off before
No, go ahead.
So I'm a big believer in team science, and you know LBL has a whole motto about team science, and most of the labs do. So the career advice I tend to give people, and I usually give to people the younger than those in the room, but the question is not what do you want to do? Do you want to, be this person or that person? I usually say you're going to be on a team. Which person on that team do you want to be? And so I think the way that we actually handle the complexity is, yes, if I'm the software engineer, I have to understand something about what the scientist is asking. If I'm the scientist, I have to understand something about the constraints of, no, I can't solve a billion cubed problem, or maybe I can. But the point is, if you're on that team, yes, you're working, the mathematicians, the scientists, the computer scientists that are working together. You're not going to be the entire team. You're going to be a person on that team, and that's where your bias comes in. And that's where, I really want to find a cure for cancer, but I want to do it by writing the code that manages the instrument, the data coming out of the instrumentation. And that's still curing cancer. So I think that the story I always tell is, if being in math and or being in HPC meant I had to invert matrices all day, I would quit. Okay? I just, I love PDEs, I always loved physics, I don't like matrices, I don't like linear algebra. So when you go into high school, it's, do I like math or I don't like math? I like science. No, that's the wrong question. I don't have to love inverting matrices because I've got Jonathan to do that, and Barry sometimes, right? So we can kind of embrace the complexity without feeling that we have to love all of it. And I think that's an important message. If you hate one part of science, that doesn't mean you shouldn't be a scientist.
Yeah.
It means you don't be that kind of scientist.
Mm-hmm.
And I think the same thing is true across HPC. Not everybody wants to write assembly code. If I had to write assembly code, I would have quit. But I think basically, if you're smart and you like this space, there is a place.
I agree with everything she said.
I'd just like to add that the SciAm activity group on computational science and engineering is a really outstanding, diverse group of people. So for those of you who are interested in high-performance computational science, I encourage you to consider SciAm, CSC, and also the supercomputing group. In my presentation this morning, I pointed out a paper that appeared in SciAm Review in August 2018 that included work by that activity group about the skills and learning outcomes that are needed for high-performance computational science. And I would say, to address your question over here, it would be wonderful for people who are considering programs for education from the undergraduate through graduate levels to consider the learning outcomes that we need, and then also to consider people's roles and what their interests are, because obviously the skills that you need to contribute as say a computational chemist are complementary to, but not exactly the same as what you need as an applied mathematician or a computer scientist. So that's one place to look for some specific guidance that comes from a segment of the community.
I'll just add, there is literally so much on the table that needs to be done, and so many interesting problems to solve. My whole life has been, pick one. We need all these things done, and so I generally get to pick the stuff that's. It's a blessing to have a kind of job where, we need all this stuff done. Pick one that you're interested in, and so that whatever motivates you or captures you, where your passion lies. Other question?
Well, at the risk of being presumptuous and offering more of a comment,
Please.
I'm wondering maybe about the aspect of people learning computing in serial and then learning about parallel computing and seeing it as this wall and different thing. But if you were reaching out to middle schoolers and you had them program a 1D model and then showed them oh, this is advection in 2D, look at this pretty picture. I think that you could introduce parallelism fairly easily by being all right, let's make this a matrix that won't fit on the memory of the computer, and teaching them what a seg fault is, and then being domain decomposition. Because our kids love breaking things, right? That's what I've heard.
Yeah, no, I totally agree, and I think it's something that, even just trying to introduce coding is the first thing, but this is something that maybe can be introduced alongside or even as an added thing that I would have never considered would be accessible earlier.
Well, so maybe this is an interesting question. I didn't touch parallelism until, of course, I was working at a national lab, but I'm kind of curious. How many people in here were coding and worrying about parallelism maybe when they were still in high school? Anyone? I see one. Okay. And undergrads in college, worrying about parallelism. Maybe 20% of the room. And then graduate school, is that when you're, okay, so most people I think are exposed to it once they get into graduate school. What do you think about that? Is that particular issue, scaling and parallelism, not deep enough into our sort of basic academic curriculum?
So I've actually taught parallelism to, I can't remember if it was 5th or 6th, so either elementary or middle, by telling them we want to add up 100 numbers. And so I can give it to one person and say, here's 100 numbers, add them up. Or I can have 10 people, give them each 10 numbers, have them add them up and say, okay, but how are we going to put these all together? Oh wait, you're each holding your own piece of paper. You have to communicate. But I don't actually think that's what we should be teaching middle schoolers or high school. Parallelism is not that hard to embrace. We've kind of made it this mythical thing, but you think about kids standing there with pieces of paper and, well, I got to give you my sum, partial sum, you don't call that. But we have to share our pieces of paper. Okay, that's distributed computing right there. It's not that hard a concept. So honest truth is I don't think we need to push this into the lower levels, because I think by the time they get to computing, it's going to be enough different. I mean, I think it's a natural thing. Parallelism can be a natural thing.
Well, so let's see. I think we have about 5 minutes left. Oh, go ahead.
So I just want to say,
by all means.
Along with what Lois had said about the SIAM activity group saying what the needs are for computational scientists coming out of undergrad and grad school. A lot of faculty at various universities are trying to make it more accessible for earlier students. So I spent the last 10 years teaching undergrads, parallel computing, et cetera, trying to make it pretty accessible. And a lot of folks at other places are trying to do similar things. So while I certainly didn't have that benefit when I was in school, a lot more people are getting it nowadays. It's not pervasive, but it is something that a lot of us are trying to work on.
Okay, we have time for maybe one or two more questions. We were talking about, like maybe parallel, and 20 years from now it'll be different. I'm just kind of curious, how many people on the panel are thinking about quantum computing as the next step? And don't.
If somebody writes me a layer, then I would have to see the quantum.
Okay, all right. Okay. How do you have a sense, for example, of we think of big and large in terms of scaling, in terms of number of cores, but of course the big data community, data analytics, they think of large and big in sort of a different way. So I'm just kind of curious, do those technologies, the sort of data analytics technologies, play into what we do, or is there some way to marry these, or will they be forever sort of separate? Anybody have any thoughts on that? Nope.
So your question is related to, I think, the important work that's all coming forward about the coupling of simulation and data analytics. So there's a lot of interesting research that's happening in that space now.
Okay.
And certainly will continue.
Okay. Certainly exciting. Any other?
And David Keyes will talk here on Thursday about that very question. So.
Oh, that's right. Thanks for mentioning that. Yeah. Okay, maybe time for one last question. Okay, well, I guess we'll go. We got to give Alp a little bit of time to set up, so we'll go ahead and thank our panelists.